Okay. And we're in chemistry. I just realized that. Let me go back and pause it again. And we're recording. All right. Okay, so what we have here is a zookeeper finds an escaped monkey hanging from a light pole. Aiming her tranquilizer gun at the monkey, she kneels 10 meters from the light pole, which is 5 meters high. The tip of her gun is 1 meter above the ground. At the same moment that the monkey drops a banana, the zookeeper shoots. If the dart travels at 50 meters per second, will the dart hit the monkey, the banana, or neither one? Okay, this is definitely a two-dimensional problem, and helps to use the right side of the pen here. All right, so let's go ahead and take a look. First thing you want to do is what when you do a problem? Draw a picture. So let's do it and get her done. And I do this too. I draw pictures still to this day, and it helps to have straight lines on this guy. So first of all, you got this is the direction that the tranq gun is going to be pointed. Okay. But what's the distance that the end of the tranq gun is above the ground? You guys remember? 1 meter. Good job. So, oops. Hooey. Try this again. There you go. So 1 meter above the ground. Monkey's going to be up here on the light pole. Do I got all the straight lines I need? Yeah, I think so. So let's go back to this guy. This could be some angle theta. This vector here is going to be 50 meters per second. This long dimension, oops, where's my undo button? That, okay. This distance here is 5 meters. This distance here is 4 meters. This distance down here is, what was it? 10 meters. There's a monkey sitting up here. And the monkey's going to drop its banana like that. That's going to be a banana right there. Even though it just looks like a dot, it's a banana. Or it's something else the monkey did. Somebody got my joke. Okay, so now what do we know? Do we know that change in x? Yep. Delta x equals what? Very good. Do we know the change in y? Actually, we don't, because we don't. The height of the banana is a function of time, and the height of the tranq dart is a function of time. Right? You guys see that? So let's call this delta y banana. We don't know that. Delta y tranquilizer. We don't know that. Do we know that time it would take for the tranquilizer dart to get over here to this side? Do we know it? Yes, no, maybe?
Yeah.
No, we don't. Was there any time listed in the problem? No. So we don't know the time. Not yet, yeah. We got to solve for it. We can find it, but we don't know it yet. What is some other information? There's that. What about velocity in the x direction? Do we know that? We sort of know that, right? We're given this, but we don't know it yet. But we got to go get back to that. Do we know the initial velocity in the y? Do we know? Nope, we don't know that either. Let's see, what other things we might need? Do we know theta?
No.
Nope. Dang, we don't know anything. Okay, that's okay. We'll take it one step at a time. But we do know the velocity magnitude. I gotta wait till this little blue circle stops. Well, that's unfortunate. All that lines up right on the. That a little better?
Yeah.
Do we know this? The magnitude of the tranquilizer dart?
Yeah.
We do. What does it equal? 50 meters per second. So we got quite a laundry list. But what's an easy one we can go after right from the beginning? Can we find this angle? That's kind of important because we need to break the vector up into x and y components, right? So how can we find this? How can we find this angle right here? What's that? We could, but I want to show you a trick. Yes, it's true. We can do tangent, the arc tangent. What will we put here? And you guys get your calculators out too, because you're going to help me along with these calculations. I'm not going to do the calculations. You guys can do that. What goes in this guy right here to give me my theta? Huh? 4 over 10. Because look where... You see that? 4 over 10. Now don't calculate this because it's going to turn out we don't actually even need to use trigonometry to do this. Because if this ratio... How am I going to phrase this here? Cosine of this same angle equals the adjacent over the hypotenuse. Do we know the hypotenuse? Actually, that's kind of a trick question because what units is this in? Meters per second. Do you notice the units of the other parts of the triangle? In meters. So can we use this for the hypotenuse? We cannot, because it's not the same thing. Now it's pointed in the same direction as the hypotenuse, but we can't use it. Is everybody, make sure you satisfy yourself with that thought. And if you did a little experiment, if you actually did the Pythagorean theorem on this, it's 10 meters squared plus 4 meters squared. That equals 116 meters. And someone go ahead and calculate the square root of 116. 10 what? 10.7 meters. That's right. Is that 10.7 meters? It's not. So you see, that's not the hypotenuse of the triangle, right? So let's go back. We're gonna resolve our vector into components. This is trank. So we got the magnitude of the tranquilizer dart, which we know, times cosine of theta, x hat direction, plus the magnitude, that same number, which is just 50, sine theta of y hat. Now, if we knew what the hypotenuse was, let's see. If we know what the hypotenuse, if we know sine, we know the hypotenuse is 10.7 meters. What is the opposite side? 4. Do you see that ratio equals sine of theta? Do you guys see that? Would you guys agree? Please satisfy yourself that the sine of theta equals 4 meters, which is the opposite of the triangle. This guy right here. I don't like it when this thing takes a long time. Sorry about the little pause here. Go away, little blue ball. There it is. That's the opposite side. We calculated the hypotenuse here. This guy is, for the length of this thing, it's 10.7 meters. So that's this guy right here. So do you see that? That this would have to, this would equal sine of theta. This, if this is the theta, that would equal that. You guys see that? Yeah. Okay. Well, if this is just sine theta here, why not just plug this ratio in up here? Could we do that? Do we have to take the inverse trig function? No. Now, do we know the adjacent? The length of the adjacent? We do. It's just 10. So 10 divided by 10.7. That was our hypotenuse. Then we just plug that guy in here. So let's do it. So I'm going to delete this guy. So I have some room to work. Let's go back over here. Okay. So now we have v, our trank dart vector here, is equal to 50 meters per second times cosine, which is, can someone divide this for me? 10 divided by 10.7. Point what? Give it to me at 3 significant figures there. 0.934. All right, that looks good. And that's in the x hat. Plus 50 meters per second. Okay, now what's this other one? This 4 divided by 10.7. Anybody? I'm sorry? I'll buy that. That's a multiplication symbol. And that's a decimal. All right, you guys want to do this? Go ahead and multiply these out. It's point. Remember, this is a decimal here. This is multiplied. What's the x component? $46 point what? And the x. What's the other one? 18.7 meters per second in the y-hat direction. Okay, now we got some information. We can start working here. Now you guys got this written down, right? I'm gonna delete all this guy. We need more room to work.
What is the x and y opposite?
That's just telling you what direction that component of the vector is pointing. I could actually delete all this. I'm getting the hang of this.
What are you solving for again?
Right now we're just breaking these up. So do we? Oh, look, hey, do we got a couple things? Yeah, we got these guys. Trash. Oh, come on, curly thing. I'm gonna start saying bad words because of this thing. There we go. No, that's not what I wanted to do here. Let's just use the eraser. They're small enough anyways. Okay. So what's the initial velocity in the x? Yeah, 46.8 meters per second. What's the y component? Yep, 18.7. Now, which one of these change over time? Do they both stay the same? Does one change, or what? Can someone tell me? That was part of the lecture yesterday. Do both of these velocities stay the same as the problem goes on, as time goes on? Does one of them change? Does they both change? Only y changes, right? But x is gonna stay the same, the velocity in x.
Why does y change?
Because gravity is affecting it. Right? Does gravity affect the x component? No, not as long as you choose the y to be pointed up and down. It does straight up and down. It does not. Now, if you choose your x and y to be at some kind of cant angle to the gravity, it's going to change everything. Okay, sweet. So since it's constant, can we calculate the amount of time for the tranq dart to get from the left side to the right side of our problem? Can we do that? Yeah, we can. Shoot. So delta x equals v sub 0 sub x times t. I'm not going to use delta t because that's kind of redundant, because we're almost always time 1 will be 0. So this is going to be 10 meters, and this is going to be 46.8 meters per second. I like meters per second times time. How do I solve for t? Yeah. So what is it? Yeah.
Where did the point inclusion come from there?
This one? This was a simplification of, from our canonical equations that I told you to memorize upon punishment of death. Is there acceleration in the x? No. That goes bye-bye. Just leaves this. Yeah?
Yeah.
Interesting. Okay. Did you guys get the answer yet? You guys know what to do, right? 10 meters divided by 446.8. The meters cancel. The second flips up on the top. Equals what? 214? Okay. 0.213 seconds. Okay, I'll buy that. So, check it out. We got another thing over here. We're narrowing them down. 0.213 seconds. Well, guess what? Now, can we find out how far the banana falls in that time? We can. What equation do we use? You don't know? Is it quadratic or linear? Quadratic. Right? Because it's got what? When do you know how to use what? Do you know when to use a linear or when to use a quadratic? When to use linear? When there's no acceleration. Is there acceleration of y? Then you got to use the quadratic displacement. That's this guy. Delta y, banana, equals velocity sub 0 sub y times t minus 1/2 g t squared. Now why is there a negative here? Gravity's pointing down. And that's just the same old equation, it's just now in the y direction and we got g instead of a. Okay? Did the banana have a y component initially? And velocity? It did not, you're right. That is a 0. So that leaves delta y, banana, equals negative 1/2 gt squared. Now here's the trick. Is this displacement going to be positive or negative? Huh? Positive or negative? It'll be negative. And that makes sense because the banana is dropping down. So, but we want to put this banana in terms of the ground. So we're going to have to do a little mathematics because right now it's going to be in turn. You guys see that the displacement is going to be relative to the monkey. Yeah. Okay. So let's go ahead and plug this in. What do we get? What's g? G equals what? Well, if g is a scalar, we'll just call it 9.8 because we already counted for the negative sign right here, so we don't want to do that twice. Maybe for a second. T, we have it up here, so go ahead and plug that in. Knock it out. What'd you guys get? Well, give me 366 so don't get rounding errors. At least minimal rounding errors. We got 228 last first period. Maybe it's maybe it is. I don't know. Okay. Fair enough. So what was it again? 223 you said? Okay. So it drops 0.223 meters. So then relative to the ground, what height would that be? So I'm going to get rid of this delta thing. So we're just solving for y now, not the change in y. If the monkey's 5 meters up and it drops 0.223, what would the y be? How about 366? Yeah. Okay, that's good. So now we don't even care about theta anymore, right? I showed you could have plugged it into tan and done all that, but that was a lot of extra work. The way I did it was a little easier, but it was kind of a trick. So we don't care about this anymore. So the only thing left, we have delta y of the Trank dart. Do we use quadratic or linear displacement equation for this? Which one, folks? Is it accelerating in the y? Yes. Because gravity, right? So do we quadratic or linear? Yes. Delta y equals v sub 0 sub y times t. Do we know t? Yeah, it's the same t, because that's the t it took to get across. So what we're trying to find is what height it is in the y after it's traveled this length of time. Because remember, we could treat time, the y and the x-axis different. So this is 1/2 gt squared. But hey, wait, didn't we already calculate this over here? We did. So this is just going to be, we don't have to recalculate this. We just have to calculate this bit here. So first of all, I'm going to separate this delta y. I'm going to call it y Trank minus y initials. What height was it initially? No, remember it's the tip of the barrel of the gun. So 1 meter, yeah. Times t minus 1/2 gt squared. So let's bring this negative 1 meter over here. So that becomes plus 1 meter. So then we can get rid of this guy. So that's just a simplification. Now we get everything in terms of y Trank. Okay. Now what's v sub not sub y times our time that we got? What is that? What is the value of that? What is it? I'm sorry, I can't hear you. 18.7? Oh, but times this number though. 18.7 meters per second times the time. Times 0.213 seconds. Minus, this has already been calculated, we don't need to do it again. Minus 223 meters plus 1 meter. So go ahead and calculate that bad boy. What'd you guys get?
4.760.
And that's rounded correctly? Well, we just had a little rounding error creep in, I guess. 4.76 meters. So what did it hit? Did it hit the monkey? What did it hit? Hit the banana. Even though it was shooting at the monkey, what's the explanation there? You guys know? Yeah, gravity's pulling on this the tranq dart and accelerating it at the same rate the banana. So they meet. And it turns out that no matter what the muzzle velocity of the tranq gun was, it still meet it. If the tranq gun is projectile, the dart is traveling at faster speed, it'll connect just further up closer to the top of the telephone or light pole. If it's going slower, just connect further down. Right? And it can also be at any distance, any angle, just so long as it has enough velocity to reach before it hits the ground. That's the only condition. And the other condition is that it has to be pointed at the monkey, and they both have to be released at the same time. So let's take a look at a video showing this. We're done with this. Well, let's just check our work before we go look at the video. Select the coordinate system. Yeah, we did that. Find this. We actually did away with this, but you see what they would have done, what they did. Find the delta T. They got 215. They got 227. So we had some little rounding things going on, I think. But pretty close. 3.76 was the dart. But remember, you got to add that other meter because the tip of the barrel was a meter off the ground. That's it. Now I'll post this video so you can go through it again because I know it was a lot. But you guys are going to be doing these too. Let's see. We're done with that. Now let's watch a video. We got the sound on? No, not yet. So see if he slows the ball down, still connect. Alrighty.
Very good, Russia.
Yes. Now go ahead and start on the problem set.